What we're going to do today is we're going to talk about more details of this pipelining thing. So let's just review a little bit. Here's the one-stage beta. This is the non-pipelined beta. Or another way of thinking about it is that this is a pipeline beta, but there's only one stage to the pipeline. And that stage is the clock that goes to these registers down here. And if you remember the idea, everything that was up here was what we called combinatorial, that as soon as this clock went off, a little bit of time would pass, but then all the data values would begin to percolate down over here and get set up over on the data inputs to these registers here. And then the setup time would pass, hopefully, right? And then you'd clock this thing again, and again the data would percolate down, okay? So that was the single stage one, and the trouble with this was that it takes too long for the data to percolate down, right? And so we decided that we're going to break this up into a number of stages, and that way we can run the clock faster. And as a result, we'll have multiple instructions in various stages of execution in different stages of the pipeline, just like an assembly line. And if you remember, we have the instruction fetch stage, the register fetch stage, the ALU stage, and the write back stage. These are all slides from the last class. I'm going to skip over this one here and go directly to this picture, which, if you remember, is how we had broken up the pipeline before, okay? Different stages here with the blue lines. And so the assumption is that there are registers going across all of these lines. Now, this all seems like a great idea, except that it has slight problems. And in particular, one example is called a pipeline hazard. In this case, it's called a write hazard. And it means that if we write the register 3 in one instruction and then try to read the register 3 in the next instruction, we have a problem. And the reason we have a problem is because this register doesn't get written until the end of the write back stage over here, and yet it is read during the register fetch stage over here for the next instruction. And this occurs, this is time going by on the x-axis here, and two instructions shown in their various stages of processing. We have the problem that this happens later than that, and so as a result, this would get a stale, an old value of R3. And that's no good because it breaks the semantics of programming this machine. The semantics of the programming are this machine should act as if each instruction runs to completion before the next one starts. So the solutions, as you recall, was first of all, you just tell the programmer, hey, this is a weird machine. Instructions don't really finish writing their results until 1 or 2 or 3 or whatever clock cycles later. So you should just avoid reading registers that get written in the previous instruction. And so as an example, a programmer might take some code like this and move this compare instruction to later on in the code so that this write has 2 extra instructions in between before we read it, and that would sort of solve the problem, because if you read this thing over here 2 instructions later, you would be reading it after it had been written to the register file, and you'd get the proper result. Therese?
Actually, this is a little bit of an aside, but I'm confused in terms of why you seem to be differentiating within the box, whether you're writing at the beginning of the box or the end. And I know
okay.
Two, and I think they almost do it backwards or something, but I don't know what.
Oh, is it backwards from what I do? Yeah. Well, let me make it as clear as I can. And actually, I think the previous diagram shows it better. Okay. I assume that these lines are the rising edge of the clock. Okay. And so when I think about when does the data actually get clocked in to that register file, it's when the clock goes off at the end of the cycle. So here, the data in the write back stage is sitting around at the D input to the register file, waiting to be clocked in. And here it gets clocked in. So it doesn't go into the file till right here. Now, when is data actually being actively read from the register file? It's during this time here, inside of this box here. And so all I need to know, really, is that if I want this to work without any fancy bypass paths, then if I write in this box here and I read in the next box in time, then I'll get the new value. Whereas if I did a read here, I get the old value. And if I do a read here, I get the old value. So actually, this red arrow here should really end kind of in this box here. So because the reads are combinatorial and the writes are done at the edge of the clock that ends the cycle, That's why I think of the write happening at the trailing edge of a cycle, and the reads is happening during this time. Okay? Whereas the read is happening during this time here. So anyway, one thing I could do is, and not all register files work that way. Some, and the Hennessy and Patterson book may talk about reads happening at the beginning of a clock cycle, for all I know. But in this machine, that is how they work. Okay. So by moving the compare down later, we assure that the value that we're going to be reading from the register file is the one that was written in this cycle over here. But that's a kind of clumsy way to do things. And if you remember, the reason is that the publisher of the data sheets for this type of processor would have to say, well, for model X of the processor, there are 2 instructions you need to have time delay. And then they come out with model Y of the processor, which typically would be higher performance but with more pipeline stages in it. And now there are suddenly more instructions of time delay between one and the other. And so in general, this kind of method of programming around it is not really used very much. Okay, at least not just by itself. Second method is to say, let's inject some no-ops or no operations into the machine for 2 clock cycles in a row, and in that way, we won't have the programmer explicitly move the instruction to later. We'll have the machine implicitly at runtime move the instruction to later by just stalling for a few clock cycles. And you guys saw how you could in fact do that by disinhibiting the writes from the PC and from the register file and the memory. That's a way to stall the machine. Another way to stall the machine is actually to, in the instruction fetch unit itself, to insert no-ops in place of the instructions that are meant to come out and just stop the PC from incrementing. Okay, and what is a no-op in this system? It's something like add R31 to R31, putting the result in R31. That doesn't do anything. And so you could inject 2 of those before this thing actually did its job. The trouble with this, of course, is that it's very slow. Right? We're basically saying don't use the pipeline whenever there is a conflict between the write back and the read. The other idea was bypass paths. And we began to get into this at the last lecture. And we said, well, you know, even though the result that we want to have over here, we want the result here, is not available until the end over here in terms of the register file, in truth, that result is being produced during this clock cycle here by the ALU. And if towards the end of that clock cycle we just directly grabbed it and moved it to over here, which is the input of the ALU for the next clock cycle, bypassing the register file entirely, let R3 get written sometime in the future. Let's go ahead and steal the value that will eventually be written to R3 over here and short circuit it and bring it over to here for this compare immediately. Then we don't have to worry about trying to move that compare to later on in the instruction stream or putting in some stalls in between the 2. And actually, in the same sense, if you look at this, this produces R0 and this uses R0. This produces R0 and this uses R0. And you'll notice that this bypass path is slightly different than this one over here, in that this one is moving forward by 2 clock cycles, and it's still not done in time for it to be read, but we could take it and feed it directly to the ALU. So in other words, if you remember, we had to, in the previous example, move the compare instruction 2 instructions later. So it's possible for us to get a conflict not only when R0 is written and then tries to be read in the next instruction, but also when it's written here and we try to read it in 2 instructions later. It's when we're safe is when there's 3 instructions of time, everything's cool. But if there's 2, we have to bypass that as well. So we need a lot of bypass paths, and let's talk about sort of the different ones. The first one we talked about in the last class was just one going from the ALU sort of up to a multiplexer on the inside of the ALU, and that's a way for data to go directly out of here and then back into here. And the key to all of this is that there is only one register in this loop, okay? And so this will allow us to use a result produced in one instruction in as data in the next instruction that's going to go in. The time delay in this loop is only one register. And I told you to think about the old unpipelined machine, or the machine which only had one stage, as not having these other three stages here, but it just had one, and there also there was one register that was inside of this big loop that the data was going around and around. So that kind of looks like this over here. We're going to take the output of the ALU, put it into a multiplexer, and then there's a register file right here, and there's only one register inside of this loop. But in the case where there are two time delays, it is possible that, you see, what ordinarily is going on here, even though there's 4 registers in this machine, there are really only 3 having to do with data that's written to the register file that then percolates back through here. So this loop over here has a problem, and it has 1, 2, 3 registers in the loop, and we just bypassed around the first one in order to reduce that to 1 register in the loop. And now we're going to put an additional bypass for having 2 registers in the loop, and this is what you do if you're trying to use the value of one instruction, not in the next one, but in the one that's 2 instructions down. Okay? And so the second level of bypass paths is something that says before something is about to be written to the register file, I want to use it in the ALU also. And thinking about how this thing works, what's going on is that we're going to clock the register file, and we're going to clock a register here, and at the same time, bang, 2 things are going to happen simultaneously. The data value will be written to the register file, and it will be latched into this pipeline stage here for use by the ALU. So the ALU will get to use it in the very same cycle when it is first available in the register file, which is still 1 cycle sooner than otherwise, in which case it would have to wait for the next cycle for it to come out of here. Let me back up just a second just to show you this on that timing diagram that we had there before. We're talking about, in this second case, not the first case which we did, which was if I produce R3 here and want to use it here, or if I produce R0 here and want to use it here. We're talking about producing R0 here and using it in an instruction that's 2 down. We're going to produce R0 here, and we're going to use it in this instruction right here. Now, why doesn't this work? Because ordinarily, R0 would be written at this edge right here, the end of the write back stage. And ordinarily, this instruction here would read the register file during this time here, and unfortunately, it just misses. This would just read the old value of R0 without the bypass path, and at the same time that this one here writes it, and so this ALU would use the old value of R0, unless we steal the value that is going to be written at the end of this cycle here, and we write it both to the register file at this time, and also steal it for use by the ALU, so they both get the new value of R0 at the same time. Does this make sense here? So this edge here clocks both of the registers with the new value of R0.
So why couldn't we have sent it from the ALU?
It's possible that this opcode wouldn't need it. And in general, a bypass path, if you think about it, a bypass path can only allow us to bypass something from one clock cycle to the next one. There's no place in the bypass path for the data to be stored. It's just short-circuiting some wires, okay? And so let's say that this opcode here used R5 instead of R0. In that case, the new value of R0 wasn't pertinent to here, and we didn't need to bypass anything. Then in this one, we suddenly need R0. But it's not the R0 that's in the register file. It's the one that's going to be written in the register file at the end of this clock cycle right here. And so what we do is that we look in the data path, and we say, where is the newest R0? So looking in the data path here, we say, where is the newest R0? We just look throughout the whole thing. Does it exist anywhere? And lo and behold, we find it sitting here waiting to be clocked into the register file. And so instead of using the stale R0 that is about to come out of here, we steal the new one that's about to be written to the register file. We peek ahead 1 clock cycle. And bypass paths always peek ahead only 1 clock cycle. But the question is, where do they peak? If they peek ahead here, then they get the value that's about to be written. If they peek ahead over here, they get the value that was just figured out by the ALU. But they're still just doing a short circuit straight here.
Why can't they peek ahead 2 clock cycles?
Well, they effectively do, but they don't keep the data hanging around for more than 1 clock cycle.
You
Okay.
could do that if you wanted, by
You could
bypass
put
path with a register.
You could put registers in the bypass path, but in general that's not necessary to do because there are already registers in the machine. And the question is, okay, so let's think about this some more. Why are we doing all the bypassing on this input to the ALU? The answer is that the ALU is where we actually have to commit to using the data. Once we've done a calculation with a data value, it's no good if we've used the old one, right? We can't do it again. So here's sort of our last chance to get it right. We're about to go into the ALU. And we say, okay, we're about to go into the ALU with a value from the register file. Is this really the newest version of that value? And the answer is, well, maybe not. If in the next cycle we're going to write a newer version, we steal it from here. If in 2 cycles we're going to write a newer version, we steal it from here. And so that's peeking ahead, sort of 1 clock cycle or 2 clock cycles, but we don't need any storage in the green line here. We're just using wires to just look ahead for the data value. Yeah?
I'm just wondering kind of how that's all managed. Isn't it
Okay. So there is a separate pipeline, okay? And what it does is it takes the instructions themselves that come out of here, okay, these opcodes, and it filters them down. So we know what instruction is currently popping out here, what the instruction was before that, what the instruction was before that, and what the instruction was before that one. So this is like a history of time where this is the oldest one and this is the newest one, the ones that are percolating down here. And they all have register fields and constant fields and stuff like that. And a bunch of logic basically just searches whenever a register is about to be used here and about to be used here. It says, do any of the older instructions in here write those registers? And the answer is, let's use the newest value that we can. So let's try to grab it either from here if it's 2 old or from here if it's just 1 old. Let's grab it from there. And so it just compares the registers that are about to be read for use inside of here with the registers that are meant to be written in this stage and in this stage here. And if they match, then it uses them. Now what if both of them match? Which one should it grab it from? How many people think that if I get a match here and here, how many people think I should grab this one? How many people think I should grab this one? All right, see? Amazing. At MIT, half of you would have gotten that wrong. Okay? Here, half of you just didn't answer. Yeah, the answer is that the newest stuff in the pipeline is at the top, and the oldest stuff is at the bottom. Okay? So the next instruction, this is the oldest, this is the next one that's going to be done, the next one that's going to be done, and the next one is going to be done. The data flows down. Okay? And so if this one is destined for R0, and this one is destined for R0, and we're trying to read R0 over here, we use this one because it's the newest write of R0. Kind of cool, huh? All right. So that's a bypass path for not quite the most recent thing, but the one a little older than that. But you know what? It's complicated because not only do we have to bypass this data that's about to be used by the ALU, we need to also consider the PC. Now, if you think about the PC and it has 1 added to it and that those values kind of go down and then the PC is written, it's a very strange machine that has an adder. Like, let's simplify this on the board right here. Okay, here's a register. Here's an incrementer. And here is a feedback path. And here's D, and here's Q. And here's this clock that keeps going from low to high. Okay, and everybody agrees that if I had a setup like this, that it would just count, right? 1, 2, 3, 4, 5, 6, 7, like we want the program counter to do. But according to that diagram, I have inserted an extra 1, 2, 3 registers in the path. And it doesn't matter where I do it, so let's put them here. 1, 2, 3. Now, let's think about how that works. So a 0 comes out here, a 1 comes out here, so there's a 1 here. But what are the values that are in here? Well, we don't actually know, right? So, but let's assume that there's 0, 0, 0, okay? Okay, the clock goes off, bang. All of the registers here, these are registers just like this one right here. So the clock goes to all of them. Okay, bang, the clock goes off. What happens?
I shift.
They shift over. Okay, this is actually what's called a shift register. And so this one goes to here, and I still get a 0 and a 0 and a 0 and a 1, and a 1 goes in here. And the clock goes off again, bang. Okay, now I get a 1 over here. I think that's right. Bang, now I get a 1 over here. Now finally, bang, I get a 1 over here, and that becomes a 2, and then 2 goes in here. Bang, what happens? Okay, now this is not working right, is it? In fact, the clock has slowed down by a factor of, 1, 2, 3, so it's like a factor of 4. It now takes 4 clock cycles for every increment of the PC. And that means every instruction here is going to be done 4 times in a row, going down through the pipeline, which will not only do the wrong thing, in terms of like if an opcode says, add R0 to R0, putting the result in R0, that'll happen 4 times, which is bad. But it also completely defeats the purpose of the pipeline, because we want the next instruction to go in. So we realize that this little finite state machine that we've built for the program counter to increment itself has a problem with pipelining. In fact, we need to steal this PC, get this +1 and move it to over here, and we need to bypass this whole thing and put PC +1 directly into here, around all these registers. Because we have to make sure that this feedback loop of PC incremented, clocked in, only has 1 register in the loop. Otherwise, we won't get the action that we want of the PC incrementing every single time. So there certainly needs to be a bypass path, in fact, a permanent one, for grabbing the PC around all of this hair here. Okay. Other things, though. What if the idea is that we are going to jump to a particular place? We're going to branch to a different place. How is that done? Well, as I recall, we say branch RA, and RA goes out to this little guy here and gets tested, comma constant, the constant goes in here, comma RC, which goes into here, and how does the constant work? The constant goes into, the constant goes into this path here. The PC +1, in this case we're going to have to steal it from this green line here, goes into this path here. They both go into the ALU, right? And then the result is supposed to go into the PC. Well, when we do a branch, we don't want to wait around very long now, do we? We want the branch to happen as soon as possible. So we need a bypass path in order to bypass as much as possible for doing the branch. So we take the branch right out of here and we feed it right into the PC. Now this sounds sort of okay, except it's not completely okay. And the reason it's not completely okay is that even though we're trying to get the result of where to branch to into the PC as soon as possible by having it jump over this register and going straight into here, what is still the case? When this guy clocks, this one will clock and this one will clock too. And into this register and into this register will occur opcodes that happened after the branch but are not from the place of the new PC. So in other words, we didn't used to have these registers. It used to be the case that when we updated the PC, the new instruction of the new place where we just branched to would begin to percolate down. But instead what happens is that the same time that we're writing the new place we want to branch to, these 2 registers are committing to executing the instructions that follow the branch but are not from the new place where we want to go to. And that sucks, okay? What it means is that if we write a bunch of code, like so, And now we say branch foo, and we have 2 lines after that, and here's foo, that when this guy writes the PC, remember the older instructions are at the bottom, these 2 newer instructions are already being latched into the pipe. Okay? In other words, we haven't, here's where we're steering to here, but we stumble on and we do these 2 anyway. And the question is what to do about that. Branch delay slots, that's what these things are called. Because in fact, branches are delayed a little bit compared to where they used to be. 1 or more of the following instructions have been prefetched by the time that a branch is taken. So, of course, the solutions pop up just like they did before. First one, program around it. We could follow each branch with 2 no-op instructions. We know what those are, right? Those are branch R31, R31. The other thing you can do is you make the compiler clever. So we tell the compiler, hey, look, chances are that this branch, in most cases, you don't actually branch forward to foo, you actually branch back to foo. And the reason for that is that this is a typical loop that is written, and software is full of loops. And loops tend to be several instructions long, 1, 2, 3, 4, 5, 6, let's say. So why not have the compiler take these last 2 instructions, 5 and 6, and move them to after the branch. Here's 5 and here's 6. Now this looks bizarre when you look at it. It's like, do 1 through 4, branch, and then do 5 and 6. Except that, of course, the programmer knows that what this really means is not branch right away to 5 and 6. It's get the machinery going so that after the next 2 instructions, you want to branch to foo. Looks good to me. And for a while, actually, programs used to be written like this. And when I worked at Lisp Machine Inc., we used to write software that was like this because we knew exactly how many branch delay slots the machine that we built had. Okay? Sounds good. Trouble is, of course, you come out with the Pentium, 10, right, the next version, right, and it has 2 extra branch delay slots compared to the old one. So now what? Right, now the programs that used to run on the Pentium 4 don't work on the Pentium 10 because you've added more branch delay slots, and that's kind of tough. And again, the solution we briefly talked about the last time still works. You give the machine all of this mechanism, okay, saying, look, I know that if, let's say, in the case of a bypass path, right, if there's a conflict between the registers, you bypass it, okay? If for some reason you can't, and we'll talk about cases when you can't, then we'll stall. So you always try to do the next best thing. And then on top of that, the writers of the compilers, so it turns out that software is not usually written in these instructions themselves. As you guys know, it's usually written in a higher level language like Scheme, right? And there's a compiler that translates that language into this lower level software. That compiler can be targeted saying, why don't you compile code for the Pentium 4 or the Pentium 10, and it will understand a little bit about the structure here, and it will try to write the code in such a way that the automatic mechanisms inside of the chip do not suddenly fire up and insert no-ops and slow the machine down. Now what you could do, if you had the Pentium 4 with 2 branch delay slots and the Pentium 10 had 3, is you could say, well, what we'll do is we will branch in this way, and unless this thing is a no-op, we'll put in a no-op of our own. Or maybe we'll actually have a new instruction, which is called branch 3, and we'll define that as a new MMX to the cubed style opcode for the Pentium 4, and that instruction will be a branch that takes 3 time delay slots as opposed to 2. But for the old branch, we'll still insert the no-op after here. What I'm trying to get across is that you can build these machines so that they have these automatic methods of stalling the pipe, and then you can build the compilers to try to not trigger them. In other words, the machine still follows the old semantics, but you can still take advantage of the pipeline if you want to. You can make the compiler smart enough to move these opcodes to after the branch. You can try to annul the instructions automatically that follow the branch, and you do that, as we talked about before, by disabling the write enable register file, write enable memory, and PC selector. When you stall the pipe, what you're trying to do is insert no ops. When you annul an instruction, you're just trying to actually cancel the opcodes that are going to happen. So if I said branch foo and opcode 7 and 8 were here, it's okay if these instructions are done as long as they don't have an effect. So if I just disable their write, then it's okay. And so if I disable write enable register file in both of these cases, then I don't have to worry about what they're going to do. All right. But again, it's nice to be able to take advantage of the pipeline instead of annulling instructions. All right, is there any way that we could shorten the number of branch delay slots? And the answer is yes, if we added a little bit of hardware. So instead of trying to wait for the ALU to do the computation, which involves taking the PC, you remember the PC came in here, the constant came in over here, adding it together inside of here, and then grabbing the result from here and bringing it down there. What we could do is we could move the adding function for adding the constant to the PC plus 1, we could move it up one pipeline stage. And we could have a parallel adder right over here, and it would take the constant directly out of here, the PC plus 1 right out of here, and then bypass that around to over here. Okay, now, how many extra pipeline stages are there before we commit to the new PC plus 1? The PC plus 1 comes from here and is written. Thus, when this register at the bottom is written, only one of the registers has fetched an instruction beyond the branch, and that's 1 here. So we could reduce the number of branch delay slots from 2 to 1 by adding extra special hardware in one pipeline stage beforehand to do this add, and then not bothering to use the ALU in order to add the constant to the PC. Okay, let me ask a question. Why would reducing the number of branch delay slots be a good thing? Anybody have a guess as to that?
Reduces the number of no-ops you have to throw in.
That's right. But we just said that the compiler could be smart enough to go ahead and move these instructions 5 and 6 to after the branch. So doesn't that solve everything? We didn't have to add no ops there.
What if the loop was only 1 long?
Aha! What if the loop is just 1 long? So it turns out that the difference between 1 branch delay slot and 2 branch delay slots is actually not that big a deal. Okay? But when you start creating more of them, when the number starts to get to 4 or 5 or 6, then it does begin to be a big deal. And so it's important to not have too many of these things because, in fact, you will run out of instructions in the loop to move to after the branch. Okay. So that's branches. Now let's talk about loads. Now, loads are a funny thing. In loads, if you remember, we're trying to read the big slow memory and we're trying to write the register file. It's sort of like the ALU. But if we think about when the load is done, let's actually, see, is it the next slide? Yeah. Here's the next slide here. What the load does is it writes a register right over here. And let's say this guy over here wants to use the register. And this guy over here wants to use the register. One would think that it should be possible to bypass the data in some way from over here to over here, and certainly to be able to bypass it from over here to over here. Except it's not quite so easy. Okay. As it turns out, we can, just as before, just before a data value is about to be written to the register file here, we can take a sneak peek at what is about to be written, and we can put it up here going into the ALU, so that when the clock goes off, this register and this register down here will be clocked at exactly the same time, and the data will go into both places at the same time. So this will get the same value that this one over here does, and we will have saved this instruction, which is right over here in terms of the write back over here and the read to the ALU. But how about this instruction? What if we load something over here and we want to process it right over here? Can we bypass that as well? In other words, in order to, right over at this time right here is where the ALU needs the value of register 4. Has register 4, has the value which is going into register 4 been figured out by this load instruction? When does this data, in fact, get ready to be clocked into the register file? Well, if you look at it, unfortunately, the memory access for the big slow memory is right over here. And in fact, this memory here does not have its data ready until right before the clock goes off here. So if in fact this load occurs, the data is not ready until here, right down here. And that means that any hope that we have of getting a sneak peek at that data in this instruction is lost. We simply cannot get this data in this add instruction because it's not available until here. And that would mean going a bypass path backwards in time, and one can't build such a thing. You can only build a bypass path that goes forward in time, as I said before, by 1 clock cycle. So at the time that this ALU is going to irrevocably utilize the data from R4, the data from R4, the newest data that we want from R4, does not exist anywhere in the pipeline. It won't exist until here. And that is difficult. And so what we have to do with this thing is give up. We have to say, problem number 2, where we're trying to use R4 when we want the latest value and there's at least one instruction in between, that's okay. We can use a bypass path to fix that. But we cannot use a bypass path to fix problem number 1, because when the read of R4 goes on, the value, the newest value of R4 has nowhere been figured out in the machine. So the only way that we could do it is to insert no ops, move the instruction to some other place, or automatically stall the machine. And again, here's a place where typically in most modern computers there is hardware inside the control of the machine that says if you try to read a register immediately after trying to do a load into the register, then it will stall the machine for 1 clock cycle in between those two. Now the compiler can try to be smart, and it can try to move the reads of the registers to a clock cycle after, so there's at least one instruction in between these two things, and thus it will never trigger the stalling mechanism in real time inside of the processor. And that's in general the compromise that is struck. The compiler tries to optimize as much as it can, but the machine guarantees that if necessary, it will slow its performance down in order to keep the semantics that the original serial machine had, that one instruction runs to completion before the next one starts. Okay? Cool? Cool. Okay, how about if your processor is even faster than that? So here's the trouble. We have 1 gigahertz processors, okay? Now, I know you guys think that SDRAM or even RAM bus runs at 100 megahertz or even faster than that. But first of all, note that that's a factor of 10 difference between the processor and the memory to begin with. That the memory is 10 times slower. The truth of the matter is that the memory systems sometimes are even slower than that, because the 100 megahertz that they refer to in SDRAM is referring to if I clock out a big block of data from the SDRAM, how often can I clock it out? What's the throughput? The latency of SDRAM is in fact much slower than that even, okay? And so one idea is, well, if it takes a long time to fetch, if the latency of a memory system is very long, then let's pipeline the memory. And let's just get many, many data values, keep the throughput of the memory high. and make the pipeline real long. But there is still a problem with that. So let's just explore that just a little bit. If we have a 5-stage pipeline instead of a 4, to allow the memory more time, what we would do is we would surround the memory with 2 sets of pipeline stages like here, and we would have 1, 2, 3, 4, 5 stages as opposed to 4, which we had before. Now this sounds good, except that you know now that this may lead to even worse trouble than we had before in terms of loads. The trouble with loads was that the data value that was going to come out of here wasn't available until several clock cycles after the load was issued. Well, if we put another pipeline stage in here, that's going to increase the number of forbidden times to use the results of the load from 1 to 2. And in fact, one can think of a memory system which is really, really slow but has a high throughput. In other words, the latency is long but the throughput is high, as being equivalent to a pipelined memory system, in this case with 40 stages of memory requests that are going through the memory system. This sounds great, except that the number of delay slots between the load that loads something in and the add that uses it is going to be as long as this pipeline here is long. Because fundamentally, if the request for a data value from the big slow memory goes in here and the value does not pop out until over here, we cannot do anything during the time that it's percolating through that depends on that data value. And thus we must wait. And there's no bypassing within here, because that's how long it takes to get the data value out. So this is a fundamental problem with systems, and it's fundamentally due to the mismatch of how slow the DRAM is in the machine to how fast the processor can be. As it turns out, the ALU these days is extremely fast. The register files are getting very, very fast. And the real problem, the bottleneck in all these things, is the memory system. Okay? Now, the lecture, I don't know if it's the next lecture or the one after that. It may be the next one. We're going to talk about caches. And we're going to talk about ways of making this system appear to be faster more of the time. But occasionally, it'll be slow. It'll be as slow as this. And we're going to have to figure out something to do when it is slow in order to not slow the machine down too much. So let's go over what we did today. You guys understand now that pipelining improves throughput. It lowers the clock period. It does not improve latency. These data hazards that we talk about, where we're trying to read a value before it's written to the register file, they can be fixed in 3 ways. You can program around them, you can stall the machine with no ops, or you can put in bypass paths, thankfully because the new values exist somewhere inside of the machine, and we can sneak a peek at what they're going to be when they do get eventually written to the register files. The branch hazards that we talked about, which were the branch delay slots, they can be fixed by reprogramming, like I showed on the board, putting the operations after the branch. You can put no ops after the branch, or you can build a machine to annul the operations that happen after the branch. Memory hazards. Well, a bypass path can fix one of them, but in general, the memory system is going to be much slower than the rest of the processor. And think about it this way. If we have lots of instructions, right? Lots and lots of instructions in the machine, and the machine gets very, very fast, we're going to rip through these very, very quickly. So fundamentally, we know there's going to be a problem if the memory system is still slow. We say load something into R0, and then we want to make use of it. There's a problem in that if this machine is so fast, the time delay from one opcode to the next cannot possibly be long enough for the slow memory to respond in here. And so we need to talk about how to handle this. And that's what the next lecture is going to be on. Okay? All right, so when I first did this thing, my son, Jacob, was taking karate, and they were very big there teaching him about balance. Balance matters a lot. Too much pipelining is bad. Okay, it's possible to get carried away with this thing. Okay, as in life. Okay, the middle road, right? If the number of pipeline stages gets too large, what goes wrong? the number of branch delay slots gets too big. That means that small loops don't work right anymore, and you need to have too many stalls in them. It also means that the amount of latency between a load and the use of the register that you're going to load gets to be too big. So balance matters a lot. And actually, I think the Hennessy and Patterson textbook, as well as actually the next one that he wrote, talks a lot about how to determine how many pipeline stages you should use. So that's today's lecture, and I'll see you guys tomorrow.